Just take a second to appreciate this, and then we'll move on. So just I hope everybody got reference to the radioactive spider in the last slide. I hope everybody knows the story already. Scientist Bruce Banner saves a kid, gets caught in the blast from a gamma bomb, yada, 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 lots of radiation, big raging green monster, great. The reality of the situation probably would have looked more like this and not the Hulk. Not really an ideal comic, not really an ideal superhero anti-hero, and if we want to get even more technical, forget this thing, it's much more likely he would look like this. So point is, radiation, not really great. Works awesome for superpower origin stories, not so much in real life. Who do we have here? Whoa, okay, put all those hands down. Everybody call out at once. I know every one of you knows this is Marie Curie and her husband Pierre, but do we know really a lot about Marie Curie? Do we know her story, her sad story in some cases? So a little bit about her. 1898, she discovers polonium and radium, naming the one after her native Poland and the other one after the fact that it radiated energy and light. 1898 to 1892, she published a lot of papers, so she's very prolific in her scientific research and discoveries. In 1903, she wins the first of her Nobel Prizes. 1910, isolates radium by itself, additionally. 1911, she wins another Nobel Prize, one of only 4 people to win multiple Nobels, and in 2 different fields to boot. In 1934, she dies of aplastic anemia from long-term radiation exposure. So didn't really work out for her. Her husband additionally got run over by a carriage outside their home. So kind of a sad story for her in the long run, but still a really important person in the world of chemistry and physics. Also a really good example of the dangers of radiation and why we need to be really, really careful when we're working with radioactive materials. We don't have time to actually watch this video at the bottom, but I fully encourage you to watch it. It's only about 8 minutes long or so, or 9 minutes long, I guess if you follow the timestamp down here. It's on YouTube. It's a great documentary based on an awesome, awesome book if you ever get a chance to read these things. Interesting stuff. It's only about a 9-minute video. And we talked a little bit about this early in the year when I did the vaping presentation for everybody. It's the one where all the girls in New Jersey have the radiation poisoning, work in the dial painting factory, and their bones basically start crumbling in their body. So it's a sad story, but a very interesting story, and also, again, very appropriate for what we're going to learn about today. All right, let's not get too cocky, physics. It's about the only thing that's awesome about you. So is anybody happy to see headlines like this? Just take a second and actually look at what these things say. Pause the video if you have to. These are really not encouraging things to see. And this is 2017, all from 2017. I could have updated this a lot more in the last 2 years, and thankfully have not, because there's some really bad news out there, and it's really not getting any better anytime soon. We don't care about our planet. Most people don't, and unfortunately, we're in real big trouble. So I mentioned that vaping presentation with the slideshow before. I'm just in the video of the girls, and it kind of plays off the last slide too, because good news, all that radium stuff in the groundwater, it's conveniently also in all the vaping products. And when new studies coming out every day with all this new stuff that no one has a clue, turns out the flavorings might be more dangerous than everything else we knew about. So that's some positive news. Moving on. There's lots of good uses for radioactive things. We use it to treat cancer, we use it to identify different diseases, we can use it to make bridges stronger and test different structures to keep them safe and secure, and we can use it in research. We can tag DNA, we can look at proteins and get some really cool information from these things. But it is also very dangerous because obviously they're giving off energy, they're giving off these particles that are dangerous to our bodies. So if you work in research with this kind of radiation, you have to log all the radiation you're using, you have to wear a little monitor that measures how much you're exposed to. I used to have a little form that, kept track of everything I had done and have a little badge that turns different color when you're exposed to too much stuff. So there are ways that are really good at kind of keeping track of this stuff and trying to keep us safe, but it's something to be aware of. You remember for earth science, carbon-14, carbon dating. We can use this radioactive form of carbon to figure out how old things are. So we use the half-life that we know how long it's going to take to break down, and we can measure the amounts and different ratios of these different types of carbon in different formerly living materials to see how old they actually were. So that's a really helpful thing in archaeology and historical research and stuff like that to see how old materials like bones and fossils and things like those are. Carbon-14 and phosphorus-32 are also used in kind of real time now as what we call tracers. You can actually attach these different molecules, to different living things like little molecules, tracer molecules, and put them into living things and see how they move through these living things. So in the picture here, you could take this radioactive form of phosphorus and inject it into the plant, and then you can actually use a little Geiger counter to test parts of the plant to see what's radioactive and almost follow the path of the material through the plant as it's moved around through this living thing. So it's called a tracer because you're actually tracing how it goes through a living thing as it's going. If anyone's ever had any kind of test done, sometimes the doctor will give you, something to drink where you actually can then drink this material, and then you go in front of the screen and it can actually kind of glow and light up and show you where the stuff is going in some cases. Now, you may be thinking, well, that really doesn't sound like a good idea. I don't want to drink radioactive material. I don't want to put radioactive stuff in my body. And that is a really good point. But the materials that are used for these tracers have to meet two criteria. They have really short half-lives. So they break down and become pretty harmless very, very quickly. And they also need to be something that's going to be gotten out of the body really quickly. So if you did watch that video with the girls and the dial painters, they were using radioactive materials that the radium was trapped in their bones, and it's not going anywhere anytime soon. It's trapped in those bones for thousands of years. They excavated the bodies decades later, and they were still radioactive. These materials that are put into living things, they break down really, really quickly, and then they're easily flushed out of the body by the digestive and excretory systems, so they don't stay in there. They get them out of the body as quickly as possible. So that's a really important feature. This is awful, but kind of funny. Carbon becomes diamond, carbon's in graphite, whatever. I don't know what this little dude at the bottom's deal is, but he's pretty funny down there, like he's giving the thumbs up, so more power to him. So if it seems like I'm rushing through this, I absolutely am, because this is the last thing in the chapter. It's really nothing we need to dwell on, and I'm also supposed to be at the senior awards ceremony thing in about a half hour to give an award out, so I need to finish this pretty quickly. I mentioned when we first started this chapter that we had some radioactive stuff in the classroom, and that you probably weren't even aware of it. You all absolutely have it in your homes too, because there's actually radioactive material inside all of our smoke detectors. So if you ever open up a smoke detector, it's perfectly safe to do. There's this little box right there, a little disc thing. And as it says, it's radioactive americium. So I'm looking at the periodic table on the wall. It's element number 95, and it's one of those ones down at the bottom. That's a radioactive material that was man-made. And the way this works is, as you see in the bottom left picture there, it's giving off alpha particles. So there's alpha particles that's always being released from this radioactive source. And there's a little beam that goes between them, and the particles can move from one way to another. If any kind of smoke interrupts that beam, then something went wrong. If there's no smoke, there's nothing to get in the way, so that nothing goes wrong with the smoke detector. As soon as some kind of smoke particles get in the way, they're going to interrupt the flow of these particles through the little passageway there between the positive and negative terminals, and that's now what's going to set the alarm off and keep us safe. So nice little small version of radioactive materials there. Has a day-to-day use in our lives. Iodine 131 is another really helpful radioactive material. So this is a radioactive version of iodine that if you inject into the body will accumulate in the thyroid gland in people's throats. Now, people, if they have thyroid cancer or different thyroid conditions, these cells are really multiplying very quickly, and the iodine will really accumulate a lot. It'll pile up, and it'll give off the signal. We can tell, okay, it's building up here. There must be something wrong with these thyroids. We can also then use it as a radioactive source to actually treat these things in the same way. So we can use it to identify the condition and also treat the condition and reduce how these cells are working, and cut down the cell numbers to try to treat this disease. So a really useful thing. This is one that often enough will show up on a reading. So of all these different types of radioactive materials, iodine 131, carbon 14, and another one we'll see in a couple of minutes, are the most common examples of things that if you're going to remember any of these radioactive materials, know these ones, because that's a really easy, quick multiple choice question on regions that if you don't remember which is which, you're just kind of out of luck. There's really no place to look it up. Technetium-99, TC99, is another one that's also quickly absorbed by cancer cells. And again, meets those criteria I mentioned before, that has a short half-life and is quickly gone rid of from the body. So you can send it into a body, it gets absorbed by cancer cells, and it can give off the radiation to try to treat those tumors and destroy those cancer cells. So it's another really helpful thing. This is not so much something I would expect you to see a question on, but our next one, cobalt-60, is something you should definitely know. So know the carbon-14 used for radioactive dating, know the iodine-131 used for treating thyroid conditions, and cobalt-60 is another really good example to know. It gives off a lot of radiation, usually gamma form, as it breaks down, and we can actually use it to specifically target cancer cells. So we can actually use a machine like this that looks like something you'd see in a Bond villain lair to identify tumors and really kind of locate and hone in on them. If you ever hear any kind of commercial on the radio or TV for cyberknife technology in cancer treatment, that's this. And you can use this really advanced computer to kind of hone in on these and zero in on exactly where a tumor is and direct this beam over here right at the spot of the tumor. You don't have to ingest anything. You don't have to give radiation all over. You can really target it directly right where you know it should be and try to get a very, very focused spot of radiation right where it needs to be and nowhere else. So as we've seen, radiation can serve a lot of different purposes, especially medically and research-wise. It can help us fight off serious illnesses and try to treat previously uncurable illnesses, but obviously there is also a lot of risk associated with it because radiation does destroy tissue. we use it to destroy bad tissue, but it also poses just as much, if not more, of a risk to healthy tissue. And in particular, if it's reproductive tissue, those changes and those damages can then be passed on to future generations. That's why we talked about today, you'll have the lead shield if you get an X-ray. And in particular, doctors typically have the lead shields that'll try to protect reproductive organs. You can't get the reproductive cells damaged, or else that could get passed on to kids potentially. So that would be really, really bad. The other thing is it's not good for the planet, obviously. Waste products and things from nuclear power plants are typically really, really bad because besides being dangerous, they have long half-lives and they stay radioactive for a really, really long time. So again, going back to that video that I hope you watch at some point, that was the bad thing there. If these materials going into the girls' bodies decayed really quickly, maybe they'd get some damage on the inside, but it wouldn't be as big of a deal. These things stayed radioactive in their bones though for thousands of years, so they're never going to be able to get out of their bodies. And obviously, radioactive power plants, all this radioactive waste, it can be released into the air, into the water, into the environment, into the ground, and that would be really, really bad, and it is bad. So that's why things like Captain Planet existed, to try to brainwash entire generations of kids, which is why I'm going to show it to my bio kids tomorrow morning too, and expose them to the awesomeness of it. So just a quick little diagram here to detail comparisons of radiation levels. I think this is a really interesting picture. I'm not going to go through and read everything. Just take 30 seconds, pause this video, look at the comparisons of these things. Look at the amount of radiation given off by someone just taking a cross-country flight compared to living next to a nuclear power plant, compared to what you get from an X-ray or living next to your uranium mine, which seems insane. And then even just having a CAT scan and how much radiation you'd have to expect to be exposed to have a increased risk of cancer over your lifetime. So just look at these numbers, compare them, and I think it's very surprising, but maybe you won't feel the same way. I understand the inherent risks associated with this picture, and I just don't care. This is awesome, and someone deserves a medal for it. 13 down, 1 to go.